Hello friends, this is the second part of our videos on the section 2.4 on the engines of neural networks. So this is going to continue our discussion about gradient descent. So it's a little bit long, but we're trying to give you at least a little bit of intuition of how gradient descent actually works in practice. You'll probably be implementing in one of the assignments at least a basic calculation of the gradients for a loss function, and then using that for a forward and backward pass in order to implement gradient descent. Okay, we'll also talk a little bit about what we mean by mini batch gradient descent in this video and some other things. So gradient descent is a very generic optimization algorithm that's capable of finding optimal solutions to a wide range of problems. The general idea, like we just discussed, is we want to tweak the parameters iteratively, so in a loop, to follow the gradients down to smaller and smaller, hopefully down to the minimal cost function that we can achieve. So this material is from another class. I wanted to add it in here to get a little bit of a better intuition for how gradient descent works than you might have gotten from reading our textbook. So it would be helpful if you've taken a machine learning class or my previous machine learning class. So here's an example, a more concrete example of a loss function. This is the standard mean squared error loss function that we might use for doing a regression problem here. So in this function, we're going to calculate our loss by right here. This is multiplying our parameters. So theta is the weight, so the parameters here, times the ith input. Right, so we multiply those. That's like doing the transformations, the matrix. This is the matrix multiplication, like we talked about. And then we subtract that from y here. So this is just simply the true, right? And we could have actually replaced this over here. This is actually the predictions of our model. So this is our y prediction over here, right? So by doing this transformation, we get our predictions as the output. We subtract that from the true label. The I superscript here means that this is for each input. So we have m inputs here that we're doing this for. So once we get the difference between those, we square those, and then we're going to average. So after we sum up all those, we average that, and that gives us a measure of loss over a batch of input samples. So m input samples as an input batch here. Okay. So anyway, I mean, this is a basic example of a loss function we could use for a regression problem. So to try and make gradient descent concrete, let's say that the function that we want to solve, that we want to perform gradient descent on is this one. So y equals 0 plus 1x. So for the inputs of x, is there that and actually what we want to solve is that when x is 0, y is 0. When x is 1, y is 1. So it's basically the line that goes through the origin that has a slope of 1. So that's what we're representing. So again, just to be clear, if we plot those, so this is the actual function that we want to try to learn using gradient descent. Okay. So for example, we can implement our cost function that we just discussed in code like this, right? So if we're passing in what the current values of the parameters are, that's what theta 1 is here, and the inputs in x and the labels in y, so these are the true labels here. We can calculate the prediction. So this is what our textbook calls y underscore predict, the predictions. That's just doing a matrix multiplication of the theta parameter times the x inputs. And then we can calculate the errors. So that's just the difference between y prediction and y true, the labels here. And then we do the sum squared error. So we square all these errors and sum those up, and then we calculate the average of those. Right? So we're just doing this is an implementation of the mean squared error that we just talked about. So for example, if our current hypothesis of theta is that the weights is just 1, so theta is just set to 1, we will see, fix that. I just forgot to run the previous cell here. So if we run the previous cell, we'll have define our cost function. So if theta is 1, we ask the cost, we get a cost of 0, because, again, if we go back and look at this, the slope of this line is 0, right? So in order to get the exact perfect answer, we need to have theta to be 1 to get so that when x is 0, we get 0, when x is 1, we get 1, when x is 2, we get 2, and so on. So if we ask for the cost for when theta is not perfect, like if a slope of 1.1 or a theta of 1.1, there's going to be a small cost. And if we set theta to be 0.5, we get an even larger cost. So that's getting bigger from where we get the minimal cost here of 1. All right. So the reason why we built the function the way we did is it's actually vectorized. So we can actually calculate the cost for a batch of inputs all in one. Well, okay, so that's not completely true. So what we're actually doing here is we're calculating the cost for a sample of different parameters. Okay, so we're not actually changing the weights at this point. We're just showing what happens if the model was different. So a set of weights from like -1 to 3 here. So if we have different thetas from -1 to 3, we get these costs for our mean squared errors here for theta. So I've got an array of theta now, and if I run it for here, these are the costs as theta ranges from -1 to 3. Okay? But to understand what this does, it helps to visualize all this. Okay, so what this looks like. So here we're actually plotting the cost as a function of the weight parameters, right? So this is the same thing like I talked about. If I can go back up to here, is we've now got our loss function, which is a function of our parameters w, right? And that's what we're plotting on this figure here, is a plot of our loss function. So you can see for our simple function that we're trying to learn, we have a cost, a loss or a cost of 0 when the parameters are 1. And as we get parameters move further and further away from 1, the loss gets bigger and bigger using our sum squared cost function here. Right? And in fact, the sum squared error is actually a smooth parabola since we're taking the square of the value. So if you use many more points, you can see the true shape of this function. It's really just a parabola in 2 dimensions here. So based on theta, the further away you get from 1, the larger the cost is. And the closer you approach to 1, the closer the cost gets to 0. So I might go a little bit quick through these next examples here. So all we're doing is making it a little bit more complex. So in the first example, we only had a single parameter, theta here. So we can extend this idea. So for example, we can have theta have 2 parameters. So it's going to be actually a tensor with 2 parameters. So in this example, you can think of these as the slope and the intercept if we're trying to fit a linear regression. So if we're trying to find the best fitting line to a set of data, linear line. Okay? So here, the only difference is that now theta is expected to be, it's still a vector, but it's expected to have 2 values in it that we can think of as the slope and the intercept of the line that we're trying to fit to the set of data here. And now also our data no longer goes through has an intercept of 0. So the equation of the line that we're trying to fit is this one now. So with an intercept of 1 and a slope of 1. Right. So now since we have 2 parameters instead of 1, we can't visualize it quite as easily, the loss function. So here, one way to visualize this is we can now plot the loss as a contour plot, right? So as theta 0 and theta 1. So remember, the best line here has a slope. So theta 0 is the intercept and theta 1 is the slope in this example, if I remembering that right. But in both cases, they need to be 1. So the loss is going to be 0 when both theta 0 and theta 1 are 1. And the further away you get to it in this two-dimensional space now, the larger the loss is going to be. So that's what this contour plot is showing. This is just another view of the contour plot where we actually take the log of the value to make it a little bit easier to see how that varies. But again, the loss is going to be 0 when theta 0 and theta 1 are both 1 for the function right now that we're trying to minimize. If you can plot this in 3 dimensions, it would look like this. So now we're doing the same plot with theta 0 and theta 1, but instead of using colors, we actually plot the loss on the 3rd dimension here, right? So it looks, the reason why that first contour plot looked the way it did is it's a bit, so in 1 dimension, it changes much more rapidly in this dimension and much less rapidly in this dimension here. But yeah, this is basically our visualizing our loss of theta 0 and theta 1 in 3 dimensions. So the purpose of this next few cells in the notebook is we want to try and build up an intuition for how, if you're able to calculate the gradient of your loss function, how you can use that to update the weights to follow the gradient to get smaller and smaller losses. So that's the whole purpose of these next couple of cells. So here again, we're doing a linear regression on a set of data points, and you'll be able to see them here. So in this case, the best fitting line occurs where we have a intercept of 71.2, so theta 0, 71.2, and a slope of 0.13, so theta 1 of 0.13 here. So if you look at this data set, basically, skip over those, but basically, the data here, I'll go down and look at these figures here from running that cell. So the data set that we're trying to fit a line to do a linear regression are these data points here, the blue ones, the house data. And the best line, that like I said, has an intercept of 71 and the slope of the 0.13. So that's this gray line that we have here. Okay. So initially, if you start off with theta 0 and theta 1 being some random value. So what we did here, so initially the very first line that's plotted here, we started off with theta 0 had a value of like 1600 and theta 1 had a value of negative 0.1. Right? So if you look at that, it had that represents this first line here. Right? But if you calculate the gradients, so looking at it, if you look back at the contour plot like we did before, if we could calculate the gradients, that tells me that I need, on the theta 0 direction, I need to move this way. So on our theta 0 direction, the gradients will tell me that if I make theta 1 smaller, the loss will be reduced, right? So so in this direction, if I make theta 1 smaller, the loss is reduced. Likewise, in this direction here, this is telling me, though, that the loss with respect to theta 1, I actually want to increase it, right? Because going in this direction, the loss is bigger if I go this way. So if I make, I mean, the loss is going to get, I mean, it looks smaller the way I drew it, but it will go towards 0 in general if we're heading in this direction here, right? So anyway, with respect to this gradient, I actually need to increase the parameter because the smallest loss, where we get loss of 0, is when theta 1 is bigger than what the first point was that we had here in the notebook. Okay? So anyway, that's what this animation is trying to give you an intuition for. So if you start at an initial random value for your parameters, but if you can measure the gradient of your loss function, that will tell you which direction, how I need to change theta 1, theta 0, and theta 1 in order to move towards the smaller and smaller losses. So eventually, after 8 or 10 gradient steps here, we get down to close to the optimal loss, which occurs when theta 0 and theta 1 are both, or actually when theta 0 is like 71 and theta 1 is the 0.13 in this example. So given that we have a loss function that we can differentiate and that we can calculate the gradients on our loss function, that allows us to perform use the 4 steps that we talked about to form what's known as mini batch stochastic gradient descent. So remember that the 4 steps that we talked about were we draw a batch of training samples and the targets, y true. We run the model on those training inputs to obtain the predictions. That's the forward pass. We compute the loss of the model on that batch to measure the mismatch between the predictions and the labels. We compute the gradients then of the loss with regard to the model's current parameters. And then we move those parameters a little bit in the opposite direction that's specified by those gradients in order to reduce the loss on the next iteration. So so it's stochastic mini batch gradient descent because stochastic means that each batch is drawn at random. So normally what we do is we draw like a random batch of 128 samples, and we do that until we've drawn all of the samples from our training data, and that's called an epoch. So we do multiple mini batches until we have drawn all of the training samples for one epoch, and then we start again for the second epoch. Okay? And when we update, we need to select a reasonable value for the learning rate. So, if the learning rate is too small, we won't converge. Okay, so basically on the diagram on the right here, from our starting point, if our learning rate is good, so when we draw our batch and we calculate the gradient, I'm trying to draw the line to represent the gradient here. This will tell us that I need to, since the gradient, the derivative is negative, I need to increase my parameter value in order to go to a smaller loss function, right? So as long as my learning rate is small enough, when you multiply the derivative times the learning rate, you'll end up with small steps, and you'll converge down towards the minimal loss that you can find for your defined loss function. Okay? So as is specified here, if the loss is too small, you should converge, but it'll just take many more steps. So you'll go lots of small little steps like this to converge, right? But if the learning rate is too big, you'll actually diverge. So if my learning rate is too big, I'll take a step that might take me like over here, right? So it's not really shown on this figure, but it could be the case that loss is not smaller, but is actually bigger than what I started. So then if I take another step based on that, I'll end up at another thing that's even a larger loss. So in that way, I can ping pong and end up diverging, never going towards a minimum, just getting bigger and bigger loss values. All right. So in the lecture notebooks, there's some examples, some actual worked out of implementations of full batch gradient descent. So another thing I'll just mention real quickly is, so if you take a random sample, that's called a mini batch. So you could just take a single sample. So that's what's known as full batch gradient descent. And that's like what we're talking about here in the first part of our notebook. So yeah, if your batch size is just one, you're just taking one sample at a time, um, and that's called true stochastic gradient descent. Okay? Alternatively, you could go on the opposite extreme, and you could at every step take a batch that has all of the training data. Um, so that's called batch gradient descent. Um, so in that case, if you take all of the training data as a sample, each update would be more accurate, but it's more expensive to calculate the gradient when you do that. So normally we do mini batch gradient descent. So we pick a random sample of the training data and do an update on that. Okay. So again, I won't go through these functions one by one, but if you look at these, though, these will give you an idea of how gradient descent is actually implemented. So in particular, if you can compute the gradient, so the gradient function here is an example of how the gradients are computed. From that, if you look at this code is exactly the same as what's shown in the textbook. So once you have calculated the gradients from on the loss function, using this gradient function, basically to update theta, you just multiply the gradients times the learning rate, and you subtract that from the current set of weights to get the updated weights. And that should move the weights in the correct direction, given that your learning rate, eta here is the learning rate that we briefly mentioned. So given that eta is appropriate value, that will move those towards getting smaller and smaller losses. Right. Okay, and one more thing I wanted to mention in the section here. So another thing, you might remember that we used RMS prop as our optimization method when we did our first example of a neural network. So usually we don't use just basic gradient descent, which just simply uses the derivative, the gradient, in order to figure out the update. So we usually use advanced optimization methods that take into account not only the gradient, but the velocity of our changes. Okay, so by taking into account, so by using these advanced optimizations that take into account more than just the gradient, we can improve the performance. So we can get to the minimum loss faster than just using the gradient alone. So usually we use the gradient plus momentum. That's mostly what RMS prop and Autograd, they're variations on this idea. So momentum addresses two issues that we can have with stochastic gradient descent. So the convergence speed and the local minima. Okay, so I kind of mentioned that if the learning rate is too small, the convergence speed will be, well, it'll take a long time to move down to the minimum. Right, if I'm taking too small a step. So by looking at the momentum, we can adjust the learning rate, or we can take into account the momentum, and that will actually make the learning rate variable, so that we will go fast when we need to go. We'll take bigger steps when we need to go faster. When we need to take smaller steps when we're close to the minimum. The other thing that we didn't see in our example of our loss function, because it only had one single global minimum, but for real loss functions, for real data, often there's going to be more minimums than a single one, and not all the minimums will be the optimal one. So by taking into account momentum, you can sometimes end up, your gradient descent can actually skip over, get out of a local minimum. So if the momentum is going fast enough, it'll go out of, skip over kind of a local minimum until it finds a deeper global minimum. It'll be more likely to settle in a global minimum than in a local. It's not guaranteed. So one disadvantage of gradient descent is you're not guaranteed to find the global optimal. So you might have to run your training multiple times to ensure that you're finding a good minimum, not some kind of minimums that are just locally good but aren't good overall for the problem. Okay, so that's the end of the second part of our videos here on the engines of neural networks. So we tried to give you an intuition of how gradient descent actually works. So a little bit about how the derivative is calculated, from a loss function, and how then, the curve of that loss function works as a signal so that you can update the weight so you can follow it towards smaller losses. Okay, so that's the essence of what the gradient does for us in gradient descent. Then we discussed a little bit some of the variations of gradient descent. So we're mostly going to be using mini batch gradient descent, where you sample take a random sample of say 100 of your samples, and you do an update, a gradient descent update on that batch. So there's kind of two extremes. You can do true stochastic gradient descent, where you just take one sample at a time. So the problem with that is that the updates are not very accurate. So you get a lot of noise if your batch size goes down to one sample. But you can think of these as a range. So for true stochastic gradient descent, you're just taking a single sample. So your batch size is 1. You can take the full sample, so that's known as full stochastic gradient descent. So that one, the updates will be more expensive, would be much more accurate. So you'll pretty much go in the right direction you need to, but it's much more costly to calculate the gradients, right? So a good compromise is a small random sample, usually like 128 samples, somewhere in that range is what we use for stochastic gradient descent. And then we mentioned the idea of momentum. So the real optimizers that we will use when we're using Keras and TensorFlow libraries are gradient descent optimization, but they're more sophisticated. So they basically usually add in the idea of momentum, and this helps to avoid local minima and also helps to speed up convergence so you don't have really long convergent times. Okay, so that's it for this video. I hope you liked it. Stick around then for the next one. We're going to go into the back propagation algorithm and talk about the forward and the backward path.